Bingo, we're back with 1 o'clock rock. And we have Shiv Sharma today. Here on Research in Manoa, Shiv Sharma, PhD, is a professor at the Hawaii Institute of Geophysics and Planetology, which is within SOWEST at UH Manoa. That's the School of Ocean and Earth Science and Technology. Thanks for coming down, Shiv.
Thank you.
This is like your 27th appearance here on Think Tank.
Probably.
I'm exaggerating. Well, thank you for being here. So let's talk about, developments in your corner of the science, so to speak, which has got a lot to do with, laser technology as part of scientific measurement, instruments and measurement. And it seems like a lot has happened. So let me go down the list of the kinds of laser technology I know you have something to do. One, LIDAR. What is LIDAR? What are you using it for?
LIDAR is an acronym for light detection and ranging. It's like radar. In the radar, we use radio waves, and in the case of the LIDAR, we use a light.
Mm-hmm.
And
same principle.
Same principle. And so you send a pulse of laser, and then you can get the measurements as a function of time, and that you convert into the distance. And so with the invention of laser in 60s, it allows us to measure the very small particles in the atmosphere. And of course, you see the laser everywhere, from the supermarket to the
PowerPoint.
CDs to the PowerPoints. Yeah. So we developed that for measuring the bog on Big Island. You can also send.
Why would you want to measure bog on the Big Island?
Because it affects the health of the people. It also affects the climate. And because the bog is generated by the sulfur dioxide emitted by the volcanoes, mm-hmm. and get converted into sulfate aerosol.
So the device will send laser pulses, mm-hmm. through the bog, mm-hmm.
but
they have to come back, don't they? You have to get a readout on them. How do you get them back?
So the particles scatter light, and by using different wavelength, you can have idea about the size of the particles and also their density in the atmosphere as a function of distance. And if you have a scanning LIDAR, then you can also map out the field of these tiny particles.
So you have one device, sends it out, mm-hmm. and to the extent the particles reflect it back, you mm-hmm. get the reflection, like radar.
Yeah, it's not really reflection exactly, but it's a scattering.
Okay, scattering.
So, it's like 4 pi solid angle scattering.
Would you ever be on both sides of the VOG? In other words, you send it out on one side and you have a receiver on the other side? No.
Yeah, that's called a transmittometer,
uh-huh.
where you look at the absorption.
Uh-huh.
But this thing goes pretty high in the sky, uh-huh. so it's hard to make the transmittometer. Yeah,
okay. But
people do make it at the ground level or at some mountains, and then you can do that too. Yeah.
So in the case of LIDAR, what's the range? I mean, how far can it go and be useful to you?
It depends on the laser power and the telescope which you use to collect the light. Mm-hmm. It can go 40 kilometers up to the thing, really? And then people are using called a ozone LIDAR, and then they can measure the ozone distribution. And so our things were to just look around the volcanoes. And also we looked at the marine aerosol. And you must be wondering why the marine aerosol is important.
Well, what is a marine aerosol?
When the breaking waves hit the shore, and the little particles spray, yeah. And then they have sodium chloride in it. And so the water evaporates and then leaves little tiny particles.
So you can measure the amount of sodium chloride, and you can learn from what's in the water in the wave.
But also you can, this was funded by the Office of Naval Research. If you have a large fog, they call it, then you can have the ship disappear. So they were interested in finding out how the marine aerosol is generated and how it moves around. And so, we were working at the Bellows Air Force Base to that experiment.
I remember Oceanit, a fellow named Russell Cheng, mm-hmm. was working on a LIDAR device mm-hmm. that would determine wind direction mm-hmm. using the same principle you're talking about. Why? For configuring windmills. wind turbines, because they have to go in a certain direction, and they get a maximum efficiency if you have if they comport with wind direction. So in order to determine wind direction, he had a LIDAR device. Has that ever gone anywhere? Have you ever heard more about that?
No, so it's called wind LIDAR.
Yeah.
And you measure it with a very high resolution. So you got the laser line, and then because the particles move around, and they got a Doppler shift, and so you can from that you can measure it. So there are different wavelengths they use. NASA Langley developing a wind LIDAR at 2 micron, and then
how big is a micron?
Is 10 to the power minus 4 centimeter.
Which is the size of an atom?
No,
It's bigger than an atom.
It's much smaller than that.
Smaller than an atom. Oh, pardon me. I'm learning every day, you know, Shiv.
Yeah, it's yeah. So 1/10 of a 1,000th of a centimeter. Yeah.
Okay.
Yeah.
Anyway.
Yeah. So yeah. So then they are using also a UV LIDAR 355, and it's then being developed in Europe, and they want to deploy it in the other planets, and also trying to apply it on a satellite, so they can measure the wind field around the Earth. Yeah.
So it sounds to me like LIDAR it's already a known technology. It's a known scientific measurement technology, but it is now coming of age. It's matured, and the uses are greater and will be greater in the future.
Yeah, so what happens is that in the old days, the lasers were big, and now the system being miniaturized. So the miniaturization, and also used to have a big computer center to process the data, because you're collecting data every, say, 100 nanoseconds, so you get a huge amount of data. So now with the advancement in microcomputers and small lasers, you can put it on a satellite. Before it was just done in a van, and then you can on the ground-based measurements. So that is really a lot of development in that area.
Yeah.
So that, and then also talking about using on Mars, on Venus, and so so that is the advancement of.
You're working on the Mars trip?
Yeah, we have this Mars 2020 rover mission.
Yes.
In that case, we are using a very small laser and the telescope, and to look at the shift in the laser frequencies. It's called Raman Shift.
We talked about that a couple of times already.
Yeah.
So can you describe for the listeners what Raman Shift is?
Yeah, so when you get a monochromatic light, when it hits the molecule, you get two kinds of scattering. One is called Rayleigh scattering, which is a elastic scattering of light. There's no change in the wavelength. And then there's a small amount of that. It shifts depending on how the molecule is vibrating, and that is called inelastic scattering, and was discovered in 1928 by Sir C.V. Raman, back in Calcutta, and he got Nobel Prize for it.
And his name was Raman?
Raman, yeah.
That's an Indian name, yeah.
Yeah.
Wonderful.
Yeah.
And now it's famous worldwide.
Oh, yes. It's being used in many areas, including biomedical research, and then looking at minerals under high pressure, high temperature, atmospheric research, and it's all over the place.
Well, let's take a look at, right after this break, let's take a look. I'm always interested in medical things. The use of, laser breakdown spectroscopy, LIBS, for detection of cervical and ovarian cancer cells, plus detection of minerals and microorganisms on distant planetary surfaces. This is very interesting. We'll take a short break.
Okay.
Shiv Sharma, researcher and professor at HIGP in SOWEST here on Research in Manoa. We'll be right back to learn more.
Aloha, I'm Chantal Seville, the host of The Savvy Chick Show. You can watch the show every Wednesday at 11 a.m. Honolulu time and enjoy how to be inspired and empowered. If you're a woman or girl, everyone is welcome, but it's really dedicated to you. And we look forward to seeing you. You can also find us on thinktechhawaii.com. See you soon. Aloha.
Hi, I'm Ray Starling, and I am co-host for Hawaii's Wednesday afternoon State of Clean Energy. And with me today is Leslie Cole Brooks, and she's going to tell you what's happening this month with our shows.
Hi, everybody. I'm Leslie Cole Brooks, the Executive Director of the Distributed Energy Resources Council, and this month the focus is on distributed energy resources. We just had a great show on smart grid technologies, and the rest of the month we're going to discuss storage, different strategies, microgrids, and then we're going to have live man and woman on the street from Verge. So it's really exciting, very informative, lively, and just worth doing. So see you next Wednesday.
Bingo, we're back with Shiv Sharma of HIGP at SOEST, talking about LIDAR, talking about lasers, neat things you can do with lasers, lots of things. So far, just to summarize, we talked about LIDAR itself, that's light detection and ranging, and there are many instruments that are being used with that, including those that can read through aerosol fields. And we've talked about Raman, R-A-M-A-N, the name of a person, which is laser-induced fluorescence, LIF. I do want to ask you about how that works. And we're now talking about laser breakdown spectroscopy, LIBS, to detect cervical and ovarian cancer cells, as well as minerals and microorganisms on distant planetary surfaces. But the medicine always really is so interesting.
Yeah.
So you can use laser, that is the LIBS, laser breakdown spectroscopy, to detect cancer cells. How does that work, Shiv?
No, I think that is it's done with the Raman system.
Oh, it's the Raman system.
Yeah,
Okay.
and so you use a microscope. It's called micro Raman, and of course optically you can see the cells in the tissues. So I wrote a proposal with one of the UH medical school person, Dr. Lori Kamimoto, and we got some funding to look at the biomarkers and the cancer. So we started this project in collaboration with the medical school people and the cancer center people, and we developed a special technique because when generally in the medical profession, they use microscope, they put the sample on a glass slide and then go through a treatment, the pathology samples. And so these cells are very small, like maybe less than 10 micron or something. And so when you fire the laser on it, you see mostly the spectrum of the glass or the chemicals they use for processing it. So we developed a method of looking at it. It was basically a mirror surface on aluminum slides, and so
It's a different kind of slide.
yeah,
A microscopic slide.
yeah, made of polished aluminum
Okay.
metal,
Okay.
so that it reflects back.
The light.
Yeah,
Okay.
and the metals don't have Raman scattering, so that was very successful. So we got some tissue samples for ovarian and cervical cancer. Lori Kamimoto is an expert in OBGYN, so she was interested in that.
Yeah.
And then we looked at it. So what happens is when the person gets a cancer, it changes the chemistry of the cells.
Yeah.
So for example, in the case of ovarian cancer, what we found, there was a beta-carotene, and then was kind of surprising because it's an antioxidant. So what happens is those cells are supposed to take beta-carotene and convert it into retinol,
Yeah.
but that gene get switched off as the cell get the disease.
Yeah.
And so the beta-carotene comes there and just sits there. And so these cells have a lot of beta-carotene.
So a healthy cell would be involved in a process.
Yeah.
Now it's accumulating. Beta-carotene is accumulating.
Yeah.
And when you see accumulated amounts of it, then you know there's something wrong.
Yeah, and so we had in tissues, we had the normal cells,
Yeah.
and we had these cancer cells. And so the normal cells didn't have the beta-carotene, other one has the beta-carotene, so it was very easy to detect.
Yeah.
Although it was hard to interpret the results.
Yeah.
But in the case of cervical cancer, same thing happens. The chemistry changes, so you can really see what's going on.
Same beta-carotene is the operative measurement.
Yeah, it gives they called a resonance Raman effect, where the signal enhances by 1,000 times, and so it's easy to pick up.
Yeah.
The beta-carotene also in the, this coral, pink coral,
Yeah.
it has got a beta-carotene in it.
Is that right?
Yeah, it's because it's a composite material generated by this organism, and some of them get embedded between the layers. So I went to a medical conference on Maui, and they want to buy a CO2 laser for surgery. And so I looked around, and there was pink coral, and I said, why is pink? And so I got, for $1, I bought 2 pieces and got it to the lab and looked at it. Oh, wow, it gave a spectrum of carotene in it. So we got a paper in Biominerals.
And this helps you read the measure the amount of carotene.
Yeah.
That was the purpose of this.
Yeah, so also the Raman signal are the fingerprints. So if you get beta-carotene in any form, in any organism or in a crystal,
Yeah.
it will give you exactly the same spectrum.
Yeah. Okay. So this takes me to beyond ovarian cells and cervical cells. Am I right to say that you were working with an OBGYN on this, but if you were working on somebody else who was working with someone else who was dealing with other kinds of cancer, you would likewise be looking at beta-carotene, concentration of beta-carotene. And the device you use, a laser device, the Raman LIF device,
Yeah.
would be able to see that concentration of beta-carotene in other cancer cells as well.
No, so it's
Not
not
true,
like that.
not
It's
true.
not true.
Okay.
Because all the diseases, like cervical cancer is completely different than ovarian cancer, although it start out on the epithelial cells, but the effects are very different.
Ah.
So although it's called cancer, but it has very different things. So like for prostate cancer, there's a prostate-specific antigen, and so you can measure that. And the idea was, I think we worked with the medical people, try to find out. So then when they have an operation and how it increases, so you can measure an effect called surface enhanced Raman scattering. So if your nanoparticles of silver or gold, the signal increases by millionfold. So you can go down and measure the concentration to very low levels, like nanomolars concentration. That's like 10 to the power minus
How small is that now?
9.
It's really small.
Yeah, very tiny. Yeah.
Way smaller than an atom.
Yeah. Not atom. I think in terms of much smaller than the grain of sand.
Okay, all right, okay. So, what I get out of this is that with this Raman technology, which I know is the one you like best, isn't it?
Well, yeah, we try to be.
It's the one you're always talking about. With the Raman technology, you can measure concentrations of pretty much anything.
Yeah, as long as there are molecules, you can measure it.
Yeah.
It comes under vibrational spectroscopy
Yeah.
and or molecular spectroscopy, where you are looking at the vibration of the atoms
Yeah.
in the molecule.
Yeah.
And so it is useful for looking at from gas phase. You can do liquids, you can do in solids, even the glass, you can find out that too.
So, and you're looking for periodic table of elements. You're looking for atomic elements, right?
No, the atomic elements we look with technique called LIBS, laser-induced breakdown spectroscopy.
That's a laser breakdown spectroscopy.
So what happens, you focus the laser, very tight spot,
Yeah.
it sublimes a small amount of material,
Yeah.
and it ionizes it. And so then you get atomic emission lines.
It actually changes the material that you're looking at.
Yeah, you just put a plasma,
Yeah.
and that it emits the lines which are specific to particular elements. And so on Mars, we are developing an instrument called SuperCam. It will have a combination of Raman and LIBS and also laser-induced fluorescence.
In the same device or three
Yeah.
different? Same device?
Yeah. you
So that way you
combine
get
it.
confirmation. You're looking in many
Yeah,
ways, so
yeah.
you really know what's going on.
Yeah.
Is the data different?
Oh, yeah,
between the three
yeah,
separate
sure,
ways?
yeah. What we developed at UH was, we have a patent on it too, a combined Raman and LIBS and laser-induced fluorescence instrument. The Raman has Raman signals are very weak, so any instrument designed for Raman can look at other things very easily. And so, and that is the technology, the our collaborator at Los Alamos National Laboratory will space qualify it, and in 2020 it will go to Mars.
Well, I want to talk about that. So you are actually designing the instruments then. You're designing the instruments and you're designing the analytic processes by which you can analyze the data that comes back.
Yeah, sure, yeah.
You're doing right here in Manoa.
Yes.
You mean with metal pieces and laser lights?
Yeah,
and
we
you
can
actually put it
prototype.
together?
Yeah, prototype with the help in the physics shop. We do that, and then the whole thing was driven by the fact that you have to make it smaller if you want to send the space.
Sure.
So then we figured out how to do it. So
How do you do it?
our spectrometer is 1/16th in size than the smallest commercial instrument, and then we use we call it intensified CCD camera, similar to your
Sure.
cameras.
CCD is the chip.
Yeah, and so what you do is there's a intensifier which you can get it to like 10 nanosecond, and it also intensifies the signal. And so we can then look at that in the time domain. We can do the Raman, and we can also the fluorescence.
This is fabulous. You're really moving at breakneck speed to put all this together.
Right.
This is how old is this technology? How long have you been working on merging these technologies together?
I think on our space instruments, I have been working for almost 16 years.
Okay.
Yeah,
And this is the
it's funded by
product
the NASA.
So, and you have a patent, at least on some of this, and I wonder if I call you from the University of Moscow, I don't know if there is a place by that name, but the University of Moscow, and I say, Shiv, I'd like to use your brand new, combination, laser technology machine. Would you let me use it?
Yeah, I think in the space business, people look for who had developed the instrument and then a bunch of instrument on a rover or on a lander. And so, for example, this SuperCam instrument is going on Mars 2020. We have collaboration with French. They are going to make the telescope and the laser, and then we will make the spectrograph and then integrate the whole thing together. So there's a lot of international collaboration.
Yeah.
Yeah. So Russians are very good. They made a lander for Venus, which is really hot and under 100 atmosphere of pressure. So we had a telecon with them, and they were interested in our technology to put in a.
So you share both
Yeah,
ways,
sure.
both ways.
Yeah, yeah.
So how far are you from having the device that will go to Mars? I mean, are you going to make it? Are you going to be ready? Is it going to be done?
We already made it, and it works in the lab. So now for going to the Mars, it requires further work. They called, the advancement in technology level. They call TRL. And so then it had to be shaken because when you shoot the thing into space, it get a lot of gravity.
Yeah. To make it
force.
strong, yeah.
Yeah. So the thing moves and things like that. And then it had to be checked. Temperature is very low on Mars. So all those things. And then the radiation is high. And so you have to get military grade electronics.
Who's going to vet it? Is it NASA vet it or somebody else?
So the JPL does some of these testing.
JPL.
Yeah, and so the instrument is developed at Los Alamos. They're putting it together because they have more engineers than UH. And then we test it there, and we send it to from JPL, and they test it and then make sure that everything works fine.
Yeah. Think it'll be okay?
Yeah, sure.
Yeah. It's your baby, isn't it?
Yeah. Yeah. Actually, I visited Los Alamos last year, and they were developing and showed them, and they gave them some tips to how to make it good work.
Good.
Yeah.
Very exciting. We should all live to 2020 so we can enjoy the product of your efforts. You're going to go down to the launch, or you're just going to watch it remotely?
Yeah, it depends.
Yeah, we'll see what happens.
Yeah.
So exciting.
Yeah.
Well, we have to, catch up with you from time to time, check on the progress.
Sure.
See how it's doing,
Yeah.
and get a handle on the fact that, the Mars trip is happening, 2020. You can put it on your calendar. That is really exciting.
Yes.
You've been with it for a while. This is going to be great. Thank you, Shiv.
Thank you.
Thank you again. Shiv Sharma, He's a professor at HIGP in SOWEST, and here we are in Research in Manoa talking about neat things we can do with lasers. We only scratch the surface.